get this stuff and the floor is yours. Great. All right, thanks everybody. Yes, so title of my talk is How Do Normal Faults Grow? It's a question that I've been thinking about for many, many years, all the time. I've even had dreams about being a normal fault and thinking about how I grow. So it's been on my mind for a while, maybe too much, you might argue. Okay, and so this is going to be work from myself as well as my co-authors, Chris and Becky, who are Imperial, Adler in Bergen, the University of Bern team, even though Frank's now moved on to Potsdam, and then a little bit of work that Nick Molnar and I started last year, and he's at Aachen now, I believe. Okay. Oh, that's not going to work. That's okay. Sorry. Nothing not working. Going great. Oh, I think you might have to. Oh, there you go. Oh, it's working now. Oh, lovely. Thanks. Just needed to give it time. Okay, so little outline of the talk. First, I'm going to give you just a little crash course in normal faults, normal fault growth, and a little bit of what seismic data is and what we use it for. Then I'm going to talk about a case study using 3D seismic data and the offshore Northwest Australia, and then talk about some fault growth using physical analog modeling. Okay, so overview. I'm sure this is going to be quite basic for all of you, but just in case not, when we think about normal faults, we take two measurements, or you could take many measurements, but the ones that I'm thinking about are length and displacement, or sometimes length and throw. So if this was our extensional fault, it would be going down this way. Length is the measurement from tip to tip. Displacement is measuring how much offset there is. And then I'm usually going to put it on a little length and displacement plot where this is that length from tip to tip there. And then these, this kind of like typical bell curve is the measurements of displacement across the length of the fault. So I'll be talking about that a lot like throughout the talk. There are a couple or several schools of thoughts on how normal faults grow. The original school of thinking was called the propagating fault model. This was kind of what was thought before 3D seismic data became widely available. And so if we were looking at this little chart right here, this is looking at map view of the fault. So like looking down at the fault trace. And this is that length and displacement view like I showed you in the last slide. So under this propagating fault model, the fault would grow with increasing length and displacement at every time. So that would be time 1, time 2. So it would just slowly grow, length and displacement, length and displacement, length and displacement. So if we're looking at this, this is just a global database of fault length and this is throw in this case. But under the propagating fault model, it would grow like this, just straight along the whole time. Now, once 3D seismic data became available, the constant length model became the more not widely accepted idea, partially accepted idea, I suppose. And under that, again, looking over here in fault map view and in displacement profile, the fault gains its length almost geologically instantaneously, and then it just spends the rest of its life just accruing displacement. So if we were looking here at our little fault database, it would go length and displacement. And of course, the hybrid fault model, which would be some kind of combination of the two, which people started talking about more in the past maybe 5 or so years, wherein the fault could behave under the kind of like propagating fault model for the first up to 25% or so of the fault's life. So it has kind of like a short lengthening stage and then a prolonged displacement stage. So kind of like a mix between the two. Okay, I'm going to be showing you some 3D seismic data. Again, I'm sure a lot of you know what 3D seismic data is, but just in case not. So 3D seismic data is kind of like an X-ray of the rocks offshore. A lot of this data was originally acquired through like oil companies, but then some lovely places like Australia, for example, make the oil companies make their data publicly available after like a certain amount of years. So it's great. We get to do lots of fun science with it. So in order to get it, you have this ship here, survey ship. It has these little hydrophones here on like a tail behind it. There's an air gun that makes a loud noise, and then the noise comes down, travels, and then it bounces in between like between a change in lithology. So when you're seeing the different lines in seismic data, what you're seeing is changes in lithology. And then this is an example of what I might look at. This is a 3D cube of seismic data. So I can kind of like slice it and dice it any way I want to. And it's really, really fun to work with. Okay, so also, how do we use seismic to understand how faults grow? We can do this with syn-rift faults, so like tectonic faults where you're getting sedimentation while the fault is active. So that would look something like this. Oh, here we have our layer cake stratigraphy. Oh, little normal fault, a little bit listric, lovely. Oh, we've got some offset. We're getting some additional sedimentation in that hanging wall. Oh, it's continuing, additional sedimentation in that hanging wall, but we still have these marker beds that are both on the hanging wall and the footwall here in green and pink. And then that continued. Oh, and then faulting stopped. And then this is our post-drift sedimentation right there. So this is what it could look like, the seismic data, or at least in a schematic. Drilled a well there. And then some people that are good at biostratigraphy can then date these different horizons. And then we're able to tell at what time the fault was what length, just by measuring at different points within the stratigraphy and then kind of like subtracting through time, or subtracting the time that we have through the biostrat. Does that make sense? Happy? Okay, cool. So great, done with the overview. Now we're going to move on to the first case study. So this is northwest shelf of Australia. So setting the scene. This is the North Carnarvon Basin, which I'm really bad at pronouncing. And one day I'm going to actually learn how to say it, but not today. So this is the North Carnarvon Basin. This was formed during the breakup of Pangea, and then it was reactivated in like Jurassic, early Cretaceous, when Greater India was rifting from Australia. So during that time, that like Cretaceous into the early, Jurassic into the early Cretaceous, we started getting these normal fault blocks that are kind of trending like northeast, southwest. So this is the full area. I was focused on the study area right here in the Exodus Plateau. Okay, and then here is some kind of like overall seismic data of the entire area. And that's going, so that's going kind of like this, that seismic data is. So we can start to get our eye in. This is that seismic data without any interpretation. This is with interpretation. Our study area is around this area. And you can see these are our normal faults in question. And where you see thickening, that's where you have that hanging wall moving down. Thickening means the fault was active. So that fault was active here, which is the Jurassic in blue, and then a little bit here, which is in the Risian, which is the early Cretaceous. So moving more into the finer scale, this is what I was working with. These are the geological ages. This is my seismic data, or a little slice from it. Everything in purple is the pre-rift. Everything in blue and green here is the syn-rift. And then everything up here without any color is the post-rift. And there were some additional, these faults came later. They're kind of like small faults that happened much, much later. So we're going to kind of ignore them. So there were 4 dates from wells given. This blue one, this, I can't tell what color, green one, purple, and orange. So we were able to get these dates here. And then the additional dates I just use kind of like, taking 209.5 minus 162.5 and divided by 4. So these dates of these horizons right here aren't perfect, but they're kind of like the best that we could do. And we can still learn a lot about fault growth, even if that slip rate might not be completely accurate. Okay, so this is what my seismic data looked like. And I'll throw some interpretation on there. Again, we've got purple pre-rift, blue syn-rift, red post-rift. And the fault that we are going to be focusing on is this one right here, which I was calling fault 2. So again, that's this one right here. Now this is a surface. So when you use seismic data, you can pick a surface across the entire cube and then just like look at it from the top. So this is a surface from the bottom of the syn-rift. This is that fault right there. And then this here is the length and throw plot across the fault going from the north-northeast on this side down to the south-southwest on that side. And this is the displacement profile at every horizon. So in order to see how much throw there was at each time, you just take, so this in blue is the start of the syn-rift. And then this in red is the end of the syn-rift. So to see how much throw there was at this time, I just take the purple minus the red, and then kind of like subtract that all the way through, which we call throw backstripping. So you can figure out at what time how much throw there was. And then to figure out the length. So anyway, that's what we're going to be talking about, or what I'll be talking about. Throw versus time comes from that throw backstripping. Length versus time comes from what we call EI analysis, which is called expansion index analysis. Not terribly important name, but all that is the thickness of the hanging wall divided by the thickness of the footwall. So basically, if they're the same, so if thickness hanging wall, thickness footwall equals 1, that means they're the same thickness, fault wasn't active, or at least wasn't active in that place. If it is greater than 1, that means that the fault was active. So we're just looking for a number over 1 on this little graph right here. So at the first between, this is called a syn-rift. This is called an isopath of the syn-rift. So that's just taking that bottom horizon and the horizon above it and the amount of space between it. And I'll show you some more of those later. But the important part here, this is just showing how much of the fault was active. So this is over 1 from here to here, all the way across. So at this time, this was the active portion of that fault. So I'm just going to go through time across all of the horizons and show you how the fault grew through time. So between the first and second horizon, it established its length quite quickly to 1.2 kilometers and like 80, kilometers, yes, and 80 meters of throw. Then between the area between the next horizons, which is between 196 and 170 million years, it grew a little bit from 1.2 kilometers to about 1.4 kilometers, continued to gain throw as well. Again, gained a little bit of length from 1.6 to about 1.4 to about 1.65, and a little bit of an intake and throw here. Slightly lengthening in the next, between the next horizons. And then here at the end, the fault actually decreases in length, which is something that I saw quite a lot across the study area and in other study areas as I've been looking at more normal faults, where the tips of the fault become inactive as the area is kind of winding down tectonically. That actually happens quite a lot. So what we're seeing here is a fairly quick lengthening stage right here. And then it gains a little bit more length throughout the fault's life and then decreases. So that's kind of following somewhat of a hybrid model plus a stage of tip retreat. So these, as I was saying before, these are called, they're actually called isochrons. So this is showing the thickness between two different horizons. So basically what you're looking at here is anything in purple, it means the fault was active because you had that extra space in your fault hanging. So purple, active, yellow, inactive. So this is that first amount of time between 209.5 million years and 196.5. So these are all of our faults, these main ones here in black. So you can see that they are quite active almost across the entire length of the fault. So even without doing like an in-depth kinematic analysis, I can look at this and be like, oh, wow, there was a quick lengthening stage just between those first two horizons. So that was about a little over 4 million years. Oh, and that's just that was just a little close up, if that's helpful. Yes. So if we were looking at this right here, we can see the purple. So the fault was active almost across the entirety of the fault. Okay, and then this is between the next two horizons. As you can see, throw has kicked up a little more, but the fault continues to be active across the entirety of the faults. Here, less faults are active. You're not really seeing all of these extra faults surrounding the main faults. And that's something that we do tend to see a lot, where some faults are favored, some faults are not, and that's kind of like due to them being like in an ideal position. So through time, there tends to be less faults with more displacement. And this isn't terribly tectonically important. This is just a delta that was coming in towards that direction at the time. And then here, very low displacement during those last few million years, and the faults have decreased in size from what they were during this package. So if we were looking at fault lengthening through time, this here is normalized time and length. So the faults, most of them reached their near final length between the first and second horizon. So that's before about 20% of the fault's life, with one exception that did have one lengthening episode. And then this is looking at throw versus time, again, normalized, and more or less, throw remains more or less steady throughout the entirety of the fault's life. So just in conclusion, at least for this case study, I'm seeing 3 stages of fault growth. We have that quick lengthening stage, so that goes up until about the first 30% of the fault's life. And of course, there is throw during that time. We have that throw/displacement stage where you're not getting very much additional lengthening, but you are accruing throw. And then that fault tip retreat stage where you're still accumulating throw, but just on a smaller portion of the fault. Okay, I've already said that. Yes, this is how the fault grew, at least in this case study. We have that lengthening stage, displacement stage, tip retreat stage. So after I did this, I was thinking, what next? So part of my work, I'm not really going to talk about this much, but this was a global database, ignore this. This is a global database of normal faults that I created and published last year. So this was about like 4,000 different normal faults looking at length and displacement. And then I plotted all of the known examples of fault length and displacement through time on top of this. You'll notice there's not very many. I only found 24 faults that were tracked through time at the time of submitting this. So that was like early 2022. I think about 2 have come out since then. But really, like, it's not looked at very much. And there are many reasons for that, which I'll talk about at the end of the talk. Basically, it's just very time consuming. And yeah, it's not very fun to do. But as you can see here though, so what these little lines are here and up there, that's just showing the trajectory of length and displacement through time for these different studies. So it kind of starts at the bottom here. Sorry, it's a little difficult to see, but then it just like follows the trajectory going up. So for example, these faults from Meyer et al. 2022, this one would have behaved under the constant length model because it's just a straight line, had its final length immediately, and then went straight up. A couple of these have their final length immediately and then go over this direction. That's the tip retreat stage. And the ones I just showed you are up here in purple. Again, my apologies, this isn't showing up very well, but showing that constant length, the hybrid growth stage. And this is all of the different faults, normalized time and displacement, time and length. So after doing this, I still had some questions because seismic data, while it is an amazing tool, it does leave a lot of questions, namely this kind of like earlier stage of fault growth. So when you're looking at seismic data, even if you have the highest resolution data you possibly could, you maybe won't even see a fault until it has 6 to 10 meters of displacement. And that's all you're going to see. So it has to, so the fault length, and that's all the way across. So even the fault tips, they're not going to be resolvable unless they're about 10, and there's about 10 meters of displacement. So obviously that early stage fault growth, it just isn't resolvable. We don't really know what's happening. So when I say that the fault has a quick lengthening stage, I mean, really all I'm seeing is from 0 to 20%, and you just can't resolve it. So I kind of wanted to dig into that a little deeper. So in order to do that, I did a bit of physical analog modeling. So I went to the University of Bern. I spent about a month there, mostly eating cheese, but also running some models. So these are what our models looked like. We had this little base layer right here. And well, this is what like the whole contraption looked like. I'll have pictures of the actual thing in a minute. So we have this fixed base layer right there. On top of that, there are alternating layers of foam and plexiglass, and that's so that we set up that foam and plexiglass, and then we contract it 4 centimeters, and then we put everything else on top, so that we can kind of like create extension by moving it out. And having that foam underneath makes the strain kind of like the same throughout the entire model. On top of that is a viscous silicon mixture, and that is supposed to it is ductile, and it's supposed to represent the mantle. And so we have 4 centimeters of that, and then on top of it there is a sand pack layer. It's like just like a quartz arenite sand, 4 centimeters, and we put it in like every centimeter. We like scrape it off so that I can look at it in kind of like an X-ray view and see what's happening. So that's what it looked like. These are our dimensions. So it's about yay big by yay big, more or less. Yes. Okay. So that is what it looked like before with the alternating plexiglass and foam. And then here's with the sand pack on top of it. We then ran it inside a medical grade CT scanner. And I say medical grade because we had to sometimes stop our models so that they could do autopsies in it, which was really fun for me. But it's also great for looking at faults. So every 2 millimeters of extension, we run it through the CT scanner, and we get like a nice CT image that I was then able to extract from the CT data, throw it into Petrel, just like I'm looking at seismic data. And in addition to looking at kind of like the internal structures, we also were able to look at the structures from above. We had some like high resolution cameras at the top that were taking photos at every millimeter of extension, and that was doing like a particle analysis. So it was able to tell when all of the sand particles were moving. And I'll show you some of those results in a minute. So this is what the final experiment looked like when it was done, or at least the one that we ended up using. We did many different model configurations. This is the one that ended up having the best and most realistic results. So this little video of that over-the-top particle analysis. Am I doing okay on time? Okay, great. Okay, it's a little fast, but this is showing from 0 to 40 millimeters. So yeah, 0 to 4 centimeters of extension. So as it's going from blue to yellow, then red, that is where the like strain is being partitioned onto the faults across the model. Let it go through one more time. Okay. Okay, so, yes, okay. So when I put this into my like seismic interpretation software, this is what I got out. Again, this is that the last scan. So this is at 40 millimeters of extension. As you can see, there are all these different faults going across here. These are little horse and robins. So it is like quite realistic to what you would see in nature. Just throwing a little interpretation on top. These are just the 3 faults that I was focused on for this part of the study. And this, Toby, look away. It's very vertically exaggerated. I'm so sorry. Anyway, so this is a cross section going across the side right here. And it's going across this fault 1, which I'm going to be talking more about. So as you can see, we have kind of like horse and robins and very closely spaced faults across here. Like all of these lines of discontinuities are all different faults. But as you can see, some of them were more active than others, like this fault 1, which has a more significant amount of throw on it. Okay, so these are some of the results from the overhead images. I know that's a lot to look at, but I'm just going to point out a few different things. So this was, again, from that particle overhead particle analysis. So just like showing when the grains were moving. So during the first few millimeters of extension, we're really only getting edge effects. Well, can you see that? Oh, you can see it, but so we're really only getting edge effects. So we're starting to get some extension here, there. So we're going to kind of ignore that because edge effects can be a little bit messy. We really want to look at the when the structures start to form in the middle of the model. So we start to get like a hint of faulting in the middle of the model from 10, definitely at 12. I don't know how well it comes across here. I'm happy to show more of these models at a later time as well if anyone's interested, where you can see it a bit better. So as we go then through time, and especially up to 22, you can see lots, or 20, sorry, millimeters of extension. You can see lots of small faults across the middle. You can really see it even better by 22 millimeters of extension. And then as we continue through time, we can just skip here to 40 millimeters of extension. Fewer faults are active than were at 22 millimeters of extension. And that's kind of like I was talking before. At early stages of extension, you have lots and lots and lots of faults. And then by the late stages of extension, only a select few are active, which I'll talk about more. So again, that's what we're looking at. And I'm just pulling fault 1 more into view for everybody because that's what I'm going to be focusing on. So as you can already tell here, this already likely started out as 2 different fault segments, and there's a relay ramp in between the 2. We're going to go a little bit more into detail. I'm just starting at 22 millimeters of extension because it's a little bit easier to see in our seismic data. So at this time were 3 different faults, all dipping in the same direction. So we had that one, that one, that one. And they were underlapping, which just means that they're not like overlapping yet. We'll go a little bit more through time to 26 millimeters of extension. They're nearing each other, still underlapping. Okay. And also I should say that this line right here is where that cross section is for both of them. Okay, up to 30 millimeters of extension. These 2 fault segments have overlapped, but the relay ramp is still intact. These 2 have not overlapped yet. Up to 34, we have a breached relay ramp here. And these 2, we ended up not having a relay ramp. A relay ramp is when you get 2 faults that are slightly offset and then they end up joining. Everyone doesn't know that. By what looks like a ramp. Anyway, these 2 did not form a relay ramp, but that's just because they grew directly towards each other. So that is Yes. Then we're going to go to 38 millimeters of extension. At this time, the entire fault is completely linked, and the first two segments are hard linked. The bottom two segments are also hard linked because we have a breached relay rack, which you can see right here, where this fault segment and that one actually like breach each other. And this is a throw and length through time plot, just kind of like what I made for the seismic data as well. And so then I was able to do like throw backstripping like I did for seismic data to see what length and throw were through time. So I have the results from the one that we just looked at in addition to two other ones. So we have, this is the amount of extension in millimeters. This is the length in millimeters. So what we're seeing isn't exactly what I was showing you in the seismic models, where we had that like constant lake / hybrid model. This is something that we're calling cyclical fault growth. So what was happening, these faults, so this is length, so they lengthen just like a little bit. See, it goes up from, 0 up to, what would this be, maybe 30, or this is going up a little bit higher. And then we get a breached relay ramp. It connects with the next segment, and that's where we get that jump. And then there's another period of time with very, very little fault growth. It connects with the segment next to it. We get that jump. So, and then here over here, we have extension and throw, both in millimeters. And throw is, there's some variation, but it's more or less the same throughout. So this is showing us that, so this is kind of like in conclusion between the two tops. Faults typically behave on like a hybrid fault model on the like fault by fault basis. How many? Oh, I'm gonna finish singing it. Okay, so on like a fault by fault basis, they tend to have that like lengthening and displacement stage that is at times quite cut and dry. But then on a fault array scale, if you're looking like across the area, they have what we call this cyclical kind of stepwise growth pattern, where you get like lengthening displacement, lengthening displacement, lengthening displacement. So it's kind of like what we looked at before, but on a wider scale. And that's what we saw in the fault growth patterns. And it's similar to what some of my colleagues have been seeing in some numerical modeling that they've been doing at Potsdam. So that's, yeah, something that's quite interesting. Okay, so moving on to a bit of future work. The reason why there are not many examples of fault growth through time is because it's a bollock. You have to like, it's a lot of clicking. Like I was getting spasms for the amount of clicking that I was doing. However, there isn't a better way yet. Petrel, Trap Tester, Geoteric, all different seismic interpretation softwares. They do have like an automated fault growth program, but me and a lot of my research team have tried all of them, and they're all really, really bad. And that's just, also faults are complicated. Like it's hard if you're going to pick your hanging wall and your footwall. Sometimes you're going to have most of the time you have quite a bit of fault drag. Where is it going to pick? It is quite complicated. However, moving forward into the future, I do not want to be picking anymore. It's terrible, and it's just not where kinematic analysis is going. So this is, I haven't taken this, I was working on this before I came here, and I'm about to go back to it, but trying a little bit of me and mostly my colleague, helped by me, has been creating a code to try and pick fault growth through time, and then kind of like run the backstripping in an automated way. And there's still some bugs with it, but it's going pretty well. Kind of like the problem as well. So for example, this is from that model that I showed you. So we have a different one of these for every 2 millimeters of extension. So the program has to be able to pick up at this point, this fault is 5 segments. And then in the next like cube of data, it's 4 segments. And the next cube of data, it's 2 segments. So it is quite complicated, but that's something that we've been trying to play with a little bit. And I think that it has some interesting potential. And I have some colleagues at Imperial that are also working to do something similar with seismic data. And it's not quite there yet, but I hope in the future to not be picking faults. And then we're just going to learn so much more about fault geometries, because there's just so much data to be had. Like even in my, in my little model that I was showing, I only did an intense analysis on 3 different faults just because time limitations. But there are many, many more that we could be looking at. Yeah, that was a bit short, but this, yeah.
Right, thank you, Bailey. We have plenty of time for questions. I think I saw Toby first.
Obviously, Toby.
Absolutely loved it. Really, really good. I think last time I saw Chris give a talk on the subject, by the end of it, I was somewhat frustrated by his challenge to the world, saying there's no such thing as a fault that accumulates over time. You're like, definitely seen some.
No, I mean, it's not a binary. I will say that more there tends to be a longer lengthening stage, but by all means, I
think
occasionally.
And same with I guess I want to ask something a bit more sideways. Are you seeing any? There are sort of potentially families of different types of faults, gravitationally derived, fault derived.
Sure.
Classic. Do you see those falling? Those have particular relationships. Brian, are you able to separate those?
I've really just been separating between gravity-driven, which gravity-driven usually is like, if there's like a salt layer or a mud layer, it's quite often like quite common to get those gravity-driven faults. I haven't been looking at gravity-driven faults, really just like tectonically driven faults, but plenty of data exists to do that, especially like North Sea areas. It's something I do want to have it yet, so I'm not quite sure what the differences would be. I think that they would behave probably more or less the same, but I'm not sure. Yeah.
Well, I've got a massive data on that one.
Lovely. Where?
South Africa.
Amazing.
Cool.
So you talked about normal faulting. Would you expect similar patterns, but similar hybrid model for let's say reverse fault or like slip fault?
I would yeah, that's a good question. I would expect similar for reverse faulting. Yes, there's even less research into reverse faulting, and that's also because seismic data for reverse faults, we don't have a ton of it because sedimentary basins are of economic value. So of course that's the data that exists. However, it's something that I think would be really interesting to look at. I think that reverse faults are going to be acting very similarly to normal faults. Strike slip would be a different beast because I guess just like thinking, if you're just thinking about a strike slip fault, how would it decrease in length? I guess it would have to like establish its length quickly because I don't know actually. Yeah, I'm honestly, strike slip faults are a bit of a mystery to me. I've thought about them a lot, and I'm just like not quite sure how they would.
Yeah. In the hybrid model, we have these cycles.
Yeah.
Because usually when I run my models and have a fault in there, there's basically a constant rate that they deform. But realizing now that's might not actually be the case. But then on the other end would be the question then: is it maybe also not just the tectonic background? So is it gravity driven or tectonic driven, but also maybe topology might favor because you look at specific basins, but maybe you're in the Himalaya and look at hard ices.
Yeah, absolutely. There's
But do you think it would be looking different then or similar if I, let's say, change lithology to something super hard compared to the
Yeah,
basics?
actually, that is something I was looking at in the paper that I had last year. There wasn't as much data on fault growth through time in rocks with harder lithologies, but they do tend to be quite underdisplaced compared to faults in sedimentary rocks. Granted, a lot of faults that, at least that I've looked at, that are in my big database, that are like volcanic and metamorphic in nature, are very young. A lot of them come from like East African Rift and Iceland. Those are quite young faults. So if they're following a hybrid model, they might have already established their length and not their displacement. So that might be why. And that's what I would expect in basically what I'm saying, what I've found, lithology matters less than time. So usually when, I have a hard rock that's under displaced, it's usually because it's in a really new rift zone. So at least in my experience, lithology matters less than time.
So, there you go. So come back later.
Yeah. Go ahead.
Yeah. So you mentioned that your study area has been reactivated. So I was wondering, like, it's obvious that these faults are sin rift.
Yes.
But is there any chance of any inherited structures in there that are contributing to anything that's going on?
Yes, absolutely.
Can you tease that out?
There definitely are reactivated, or at least, well, okay, I don't have evidence for these specific faults being specifically reactivated because there's not like a double sin rift package. However, we do know that the area had extension in the like Permian during the breakup or at the end of the breakup of Pangea. So there's a high possibility that not that the faults were necessarily reactivated, but that, general trends were reactivated and possibly even the same structures. Throughout my looking at different faults, it's actually quite hard to find a virgin fault that is in an area that hasn't been reactivated. So it's kind of hard to figure out how that would affect fault growth. I believe that it makes it establish its length even more quickly because it has that plane to just like easily reactivate. But I can't say for sure on these specific ones because there's not that like double sin rift package, knowing that it's the same surface. But I would assume that it's going to establish that length even more quickly then.
Fault shortening, is that like an annealing process, or is that some sort of bigger elastic process at the end?
Yeah, I think that kind of like, so when, or at least this has been my theory and I've talked to other people about it. Once you start like, as the like tectonic activity kind of starts to die down in the area, the weakest part of the fault is going to be in the middle. Well, not always. Sometimes there's going to be like two like zones with like high deformation, but generally it's quite, towards the middle. So I think that's going to be the area that's going to remain taking up the most displacement. And then the edges are just kind of going to die off a little bit. And that's not the only place. Well, it wasn't really published much before I published that paper. But then once I posted about it on Twitter about tip retreat and then talked about it at TSG, not everyone, I probably had like 10 people being like, I've seen tip retreat in my seismic data as well, or in the field. So I think that it is a phenomenon that happens, but not on every fault, but on some faults. It definitely is something to think about.
All right. So I have questions for the days that maybe with the X-Men or data, if you saw any effect of sedimentation on the essentially growth of your fault, because clearly you have sedimentation happening in the basin.
Yes.
But is there a threshold that, like, with respect to that growth history?
Yes, absolutely. So it's really okay. At least I think this is going to answer your question. Let me know if it doesn't. It's really important that you don't have a sediment-starved basin. So, like, if you're not, if you don't have enough sedimentation in the area to fill up that basin and get some sedimentation in your footwall as well, you're not going to be able to say anything about the growth history because that's what we're, it's what we're relying on, is getting some sedimentation in both the hanging wall and the footwall. So if there's not enough sedimentation, then it's just not going to be an area that we can do any kind of kinematic analysis. Did I answer your question? Or are you saying if there's additional?
Yeah, like additional.
Mm-hmm. Mm-hmm.
Different stuff.
Mm-hmm.
They potentially shut off or shape the architecture structures that you're forming. So
yeah. I don't know. I haven't thought much about that. I'll have to talk about it later. I'm not sure. I'm not sure. I have to think about it.
I guess what inspired the question was
Yeah.
massive delta.
Yes. Yes. Yeah, in that case, you still can like pick out the amounts of displacement, but there's just like a ton of extra thickening on both sides, but you're still getting increased thickening in that hanging wall compared to the footwall. So you can still get those measurements. However, when you look at that isochron that I showed you, I might just go back to it. Okay. Come on. Okay, so you can still get all of that, like the fault's still kind of behaving the same way between here and there. There's just like so much extra sedimentation that it's really the key that's thrown off. So if I like slice this in half right there and then had like a different threshold between here and there, you'd still be able to see that fault behaving the same way. It's just, I guess, for this, maybe that's something I should do as well, cut it in the middle. But I mean, I'm not going to because I've published in 2021. But in the future, that's something to think about. It's a good thing to think about. So no, it didn't really affect the fault's growth. It just affected the visualization.
Yeah, but they stole it about the temperature.
Yeah. Yes. Yes. Yeah, that's actually a good question. Sorry, I didn't say like that's actually like you wouldn't normally. No, but that's yes, that is a good question. And actually, if you look at this one right, this big one, an example from the seismic data, and I noticed this from the seismic data before I was looking at the models, of course, because usually it kind of has been assumed that the tip dies out, but it doesn't necessarily. In this one, it's a bit hard to, I know you can still see it. Okay, a little bit. If you look right, so this is this big fault right there. I guess it might be a bit hard to see, but you have one segment that comes like this and kind of like comes out. And then this one has a breached relay ramp in between the two. And that happened between the first and second horizon, so really early on. But this little tip remained active at least until the end of, so be up to 142 million years. It remained active because which you can see here, because it's still purple on the outside of it there. And then I saw that in the models as well. Even when you do get that breach relay ramp, not always, but a lot of the time, the fault is still active on that little tip. Yeah.
I have a question. So this kind of put it on the question with our talking. So you best strip the penetration to remove.
Yeah.
Then how can you say this is a great question, but like how can you identify or ignore the component that maybe some of that photo is because of texture, because of having all of that sediment there?
Yes.
We know that texture is very important.
Yes.
Look at like transit monitoring. A lot of substance because
absolutely. There was a paper in, I'm forgetting the name of it. There was a paper in 2008, one of, a former basins person at Imperial, where they found that can account for up to 20% of a change in throw. So usually it's not that high, due to decompaction. Usually it's not that high, usually it's a lot lower, but because of that, I put an error bar, at least I didn't show it on the presentation, but in the paper, I put an error bar of 20% for all of that. However, again, this is just part of the error of seismic data. So you have some error with decompaction that could make the fault look, let me see, under displaced. Yes, okay, decompaction can make the fault look under displaced. And then not being able to visualize the tips could make your fault, or definitely does make it look shorter. So there's kind of like a bit of error on the length due to resolution. There's a bit of, or a bit to more than a bit of error due to decompaction and what you're talking about. And I just add in an error bar usually, but that is something to think about. And it's worse with, I believe they said it was worse with finer grain sediments, which luckily this isn't too fine grained, so it's not going to be up to that 20%. But yeah, that is a hard one to, yeah. However, at least when we're looking at, I mean, I would probably have to do more thought about decompaction if I was trying to drill this area. However, if I'm just thinking about fault growth, it doesn't, if I'm trying to figure out fault growth patterns, the fault growth pattern stays the same, no matter if there's, a discrepancy between the amount of growth being done. That makes sense.
Any more questions? In that case, let's unveil again.